Virtual memory concept implementation. At the end of this lesson, you will be able to explain virtual memory and explain virtual memory address translation. Introduction to virtual memory concept implementation. RAM plays a vital role in modern computers. The more RAM your CPU has access to, the more faster the computer works to produce results. Insufficient RAM leads to severe impact in the computer's performance. Consider a processor that issues 32-bit addresses as an addressable space of 4 gigabytes and a RAM of 1 gigabyte. A program arrives to be processed and the processor starts computation. The address 0 is directly mapped over to address 0 in RAM, 1 to 1, and so on. During computation, it is seen that the program does not completely fit into the main memory. If we try to access more RAM than we actually have, our program will crash. To deal with this problem, the concept of virtual memory was introduced. The concept of virtual memory in computer organization is that it allows the processor to run large, sophisticated programs even if it has a relatively small amount of RAM. It acts as a middleman between the processor and the main memory. Interesting, right? Let's learn more about it in today's session. When there is no sufficient memory, the parts of the program not currently being executed are stored in the secondary storage device. Of course, all parts of a program that are eventually executed are first brought into the main memory. So it is obvious that the part of the program in the secondary storage device is brought to main memory at some point of execution. Note that the program execution is a step-by-step process and the order cannot be changed. So, if parts of the program are stored in different locations, such as main memory, hard disk, etc., it interrupts the flow of program execution. To avoid this, the virtual memory allocates contiguous locations for the program by creating virtual addresses, which can be mapped with the actual location of the program, either in the RAM or secondary storage. In the example, we see that program 3 is stored in the hard disk. Before execution, it has to be brought to the main memory. Because of its flexibility, virtual memory moves a new segment of a program into a full memory and replaces it with another segment already in the memory by using LRU replacement algorithm. So, program 0 is replaced with program 3, since program 0 is the least recently used. Therefore, virtual memory provides an illusion to the programmer that the computer has enough primary memory left to run the programs. The techniques that automatically move program and data blocks into the physical main memory, where they are required for execution, are said to be virtual memory techniques. The displayed image gives a diagrammatic walkthrough of the virtual memory system. A special hardware unit called the Memory Management Unit translates a virtual address into a physical address. A virtual address is an address space used by the programmer. A physical address is an actual physical memory address space. When the required data are found in the main memory, then they are fetched to the cache memory for further processing. If required, data is not found in the main memory, the MMU, with the help of the operating system, brings the data from disk storage to main memory. This transfer of data from secondary memory to primary memory is performed using Direct Memory Access Scheme, which is a feature of a computer system that allows accessing the main memory by certain hardware systems. Having understood about virtual memory, let us next discuss about its address translation. A virtual memory address translation method is based on the concept of fixed length page. A page is a block of words that occupies contiguous locations in the main memory. Pages commonly range from 2K to 16K bytes in length. Take a look at the displayed diagram, which shows a typical virtual memory address translation. Each virtual address generated by the processor, whether it is in for an instruction fetch or an operand fetch, it is interpreted as a virtual page number, followed by an offset that specifies the location of a particular byte or word within a page. Information about the main memory location of each page is kept in a page table. This information includes the main memory address where the page is stored and the current status of the page. To indicate the location of the page table in memory, the hardware includes a base register that points to the start of the page table and is known as page table base register. By adding the virtual page number to the contents of this register, the address of the corresponding entry in the page table is obtained. The contents of this location give the starting address of the page if that page currently resides in the main memory. An area in the main memory that can hold one page is called a page frame. A page frame is a storage unit within the main memory, while a page is the contents in the frame. Each entry in the table also includes some control bits that describe the status of the page while it is in the main memory. The control bits indicate various restrictions that may be imposed on accessing the page. For example, a program may be given full read and write permission, or it may be restricted to read access only. The page table information is used by the MMU for every read and write access, so the page table should be situated within the MMU. If the page table is large, then it is impossible to include a complete page table on this MMU. Therefore, the page table is kept in the main memory. However, a copy of a small portion of the page table can be accommodated within the MMU. This portion contains table entries that have been most recently used transactions. A small cache, usually called the translation Lookaside Buffer, is incorporated into the MMU for this purpose. Now, let us discuss about TLB in detail. A translation Lookaside Buffer, that is, TLB, is a memory cache that stores recent translations of virtual memory to physical addresses for faster retrieval. The display diagram shows a possible organization of a TLB where the associative mapping technique is used. The operation of the TLB proceeds as follows. Given a virtual address, the processor examines the TLB if a page table entry is present. The frame number is retrieved and the real address is formed. If a page table entry is not found in the TLB, the page number is used to index the process page table. TLB first checks if the page is already in main memory. If not in main memory, a page fault is issued. Then the TLB is updated to include the new page entry. A page fault occurs when an instruction accesses a memory operand that is not in the main memory, resulting in an interruption before the execution of this instruction is completed. The address translation process in the MMU requires some time to perform, mostly dependent on the time needed to look up entries in the TLB. Thus, TLB is used to reduce memory access time as it is a high-speed associative cache. Conclusion. Hope you are clear with the concept of virtual memory. Catch you in another session. Stay tuned. Let us summarize what we have learned. The techniques that automatically move program and data blocks into the physical main memory where they are required for execution are said to be virtual memory techniques. The displayed image gives a diagrammatic walkthrough of the virtual memory system. A virtual memory address translation method is based on the concept of fixed length page. A translation look-aside buffer, that is, TLB, is a memory cache that stores recent translations of virtual memory to physical addresses for faster retrieval. TLB is used to reduce memory access time as it is a high-speed associative cache.